Hello, my name is Hossein Tabatabaee. I'm a PhD student in Computer and Communication Sciences at EPFL in Switzerland. And today I'm going to present a work performed with Professors Jean-Yves Le Boudec and Marc Boyer. So let's start. Weighted round robin, or WR, is a scheduling policy that is often used in different fields, in communication networks, networks on chips, and real-time systems. And this is because it's a very simple scheduler. With weighted round robin, we have several flows or clients, and we want to share a bandwidth or a resource among them. To do so, each queue is given a weight, which is a positive integer. Then the server visits these queues in a round-robin manner. When a queue with weight W is visited, it can send up to W packets. So let me give a very simple example of a weighted round-robin scheduling. Here, I assume that we have three different flows, flow A, flow B, and flow C. These flows have the corresponding weight. Flow A has weight 1, flow B has a weight 3, and flow C has a weight 4. And we're going to run the weighted round-robin scheduler to serve these packets of them. For example, I assume that flow A has packets A1 to A4, and I don't assume any new incoming packets for them. So what the server does is first visits queue A and serve one packet of A. Then it visits queue B. Since queue B has weight 3, it serves 3 packets of B, and lastly 4 packets of C. This is one completely weighted round robin where all flows are visited once. They have one emission opportunity where they can send several packets with respect to their weight. Then the server repeats the same algorithm to serve all other packets, which means, for example, 1 packet of A, 3 packets of B, 2 packets of C, because it has fewer packets, and so on. So it is a very simple scheduling. However, it has a non-smooth bursty service. As you can see, since the server serves several packets of one flow consecutively in the output, it results in a bursty, non-smooth service. You have 3 packets of B, 4 packets of C consecutively in output. An alternative is to use a variant of weighted round robin, which is called Interleaved weighted round robin, or IWR. With Interleaved weighted round robin, a queue with weights W is visited W times in each round rather than 1 time, and it can send up to 1 packet in each visit. So the idea is to spread packets of one flow within a round to achieve a smoother service. So let's run the Interleaved weighted round robin scheduler to the same example to see what the differences are. With the Interleaved weighted round robin, we first break one round to some mini round that we call them cycle. In this example, we break one round to 4 cycles. Flow A, flow with weight 1, only has an emission opportunity in the first cycle, and it is ignored by the server in the rest of the cycles of a round. Flow B, flow with weight 3, has emission opportunities in the first 3 cycles, and it remains silent in the last cycle. Generally, a flow with weight W has emission opportunities in the first W cycles, and it remains silent in the rest of the cycles of that round. So what the server does here, it first runs the first cycle, 1 packet of A, 1 packet of B, 1 packet of C. This is the first cycle. However, in the second cycle, only B and C has emission opportunities. So 1 packet of B, 1 packet of C. Third cycle is the same, and lastly, last cycle with 1 packet of C. This is one complete round of an Interleaved weighted round robin, and as you can observe, this is the Interleaved version of the weighted round robin output. Interleaved weighted round robin and weighted round robin has the same long-term performance. For example, at the end of the round, we have 4 packets of C, 3 packets of B, 1 packet of A for both of them. However, within a round, the IWR changes the order of the packets of flows, which gives a smoother service. Then the server repeats the same round to serve other packets. Interleaved weighted round robin has the same simplicity of the weighted round robin, which is very interesting. and it achieves a smoother service as well. Why a smoother service is interesting? Because a smoother service can result in a lower latency. For example, consider flow C, and specifically packet C1 with weighted round robin. This flow should wait for all other queues to be visited and send some packets with respect to the rate, which is in this example, it should wait for flow A and B to send 4 packets. However, in interleaved round robin, it should wait much less and should wait only for 2 packets to send packet C1. So we expect that the interleaved round robin would reduce the worst case delays. We capture this problem using a network calculus framework, which I'm going to give a quick introduction to it first. Network calculus framework heavily relies on 2 abstractions, arrival curves and service curves. By means of an arrival curve, we upper bound the amount of data that a flow can generate. Such bound is necessary to obtain bounded latency, because otherwise, if a flow can generate unlimited data, we can always congest the system in a way that the delay is arbitrarily large. We say that flow R is constrained by arrival curve alpha if in any time interval, the input of flow I in this interval is upper bounded by the alpha of the duration of the interval. Token bucket arrival curve with burst R and rate R is a frequently used arrival curve. We then lower bound the service offered by the system by means of a service curve. We say that a strict service curve is a specific kind of a service curve, and we say that the beta is a strict service curve for a flow if in any time interval that the flow is backlogged, the service offered to this flow in this interval, the output of the flow in this interval is lower bounded by the beta of the duration of the interval. Rate latency strict service curve with rate R and a latency T is a frequently used service curve. Then, if we have a flow R that is constrained by arrival curve alpha, traverse a system that offers a service curve beta, the delay that this flow experiences in this system is upper bounded by the horizontal deviation of the arrival curve of the flow alpha and the service curve of the system beta. This bound is valid for a system that is lossless, so nothing is lost here, and it preserves the order of this flow, so it is a FIFO system. For example, if the flow is constrained by a token bucket arrival curve, and the server offers a rate latency service curve, this horizontal deviation can be easily computed. In the rest of the presentation, I'm going to give you a novel strict service curve for the interleaved round robin. We're going to compare it to the state-of-the-art previously published weighted round robin strict service curve. We're also going to compare the obtainable delay bounds from this service curve. And we have some tightness results for both a strict service curve and delay bounds. So let me start with the state-of-the-art and specifically weighted round robin strict service curve. Assume that we have a server that uses the WR as a scheduling policy and receives some flows as an input. Flow I, flow of interest, with weight WI and a minimum packet length LI min. Other flows, for example, flow J, with weight WJ and a maximum packet size LJ max. We also assume that the server offers a strict service curve to the aggregate of the flows beta. Then beta I prime is a strict service curve offered to flow I in this system, which is the min plus convolution of a unit rate function with a staircase function. Let me illustrate this service curve. So for a system of 4 input flows, where we have the corresponding values for the flow of interest and other flows, where we assume that the server is a constant rate server with rate equal to C, the red curve is a strict service curve offered to flow I, flow of interest, where, as you can see, this flow should wait for all other flows to be visited and send some packets with respect to their rate. Then it has one emission opportunity where it can send W packets as well. This is first round, this is second round, this is the third round, and so on. So this is the state-of-the-art previously published strict service curve for weighted round robin we have found a novel strict service curve for Interleaved beta round robin. We have the same assumptions, but we assume that the server uses IWR as a scheduling policy rather than WR. Then beta I is a strict service curve guaranteed to flow I in this system. So the good news is our strict service curve is well defined and has a closed form with these definitions. However, you may think that it's a little bit complicated to express, which is a problem that I'm going to address further in my presentation. But let me first illustrate this strict service curve. So for the same flow in the same example, the blue curve is the Interleaved beta round robin strict service curve. As you can observe, this flow should wait for an amount of time to serve a packet, again should wait for another amount of time to serve another packet, again another packet, and so on. This is round 1, this is round 2, this is round 3, and etc. So this is the new novel strict service curve for the IWR. We know as a state-of-the-art strict service curve for WR. Now we can compare them. We have shown that the IWR strict service curve always dominates the WR strict service curve. Therefore, network calculus delay bounds for Interleaved beta round robin are guaranteed to be less than or equal to the delay bounds for beta round robin. So let me illustrate it. So for the same flow in the same example, the blue curve is the Interleaved beta round robin strict service curve, and the red curve is a weighted round robin strict service curve. And you can observe that the blue one always dominates the red one. It means if, for example, the flow of interest is constrained by some token bucket arrival curve, we can then find the horizontal deviation between these arrival curves and these service curves. It gives us delay bounds. You can observe that depending on where the burstiness of these arrival curves are, Interleaved beta round robin delay bound is strictly less than beta round robin delay bound, or sometimes it is exactly equal to the beta round robin delay bound. So let me come back to another problem that we had before, that it is the blue curve, the Interleaved beta round robin strict service curve is complicated, and it's complicated in a sense that it's complicated to express. So if someone is interested in a simple approximation, which are rate latency strict service curve, we have found the set of all non-dominated rate latency service curve. Here, I'm going to present only the one that achieves the minimum latency and only the one that achieves the maximum rate. And let me illustrate it. There are two possible cases for a set of rate latency strict service curve for a flow in IWR system. In possible case 1, we have one single best rate latency, one optimal rate latency for a flow, the green curve here. This rate latency is optimal because it achieves the minimum latency as well as the largest rate at the same time. However, sometimes there is no single best rate latency. For example, this one here. In this example, the green one achieves the minimum latency, however, it has a smaller rate as well. On the other side, the light blue strict service curve has a larger rate, but it has a larger rate with a larger latency. Sometimes the green is better, sometimes the blue is better. This is why we have a set of non-dominated rate latencies. Very well, until now, we have found a novel strict service curve for Interleaved beta round robin, but you may ask that, can I find a better strict service curve for Interleaved beta round robin? So the answer is no. We have shown that our strict service curve is the best possible one, is the largest strict service curve for flow I in this configuration. Specifically, we have shown that for any flows of the system, there exists a trajectory scenario where in a backlog period of the flow of interest, the service offered to this flow by the system is exactly equal to its strict service curve. Basically, the inequality that we have for a service curve becomes an equality. Therefore, every other strict service curve for this flow is upper bounded by ours. We have shown that the same result is also valid for the beta round robin strict service curve. So the previously published beta round robin strict service curve is also the largest one. Unfortunately, obtaining the largest possible strict service curve doesn't automatically imply that it gives us the best delay bounds, the delay bounds that are equal to worst cases. This is because, first of all, service curves are only an abstraction of the system, not a true thing that happens. The true thing that happens is the interleaved weighted round robin, or whatever the system is. Another reason is that we have found the strict service curve, which is a specific kind of a service curve. So there might be a better service curve that is not strict. Fortunately, we have shown that we have tight delay bounds for a flow with constant packet sizes. So if flow I, flow of interest, only generates packets of constant size, L, which means minimum packet size is equal to the maximum packet size for this flow, then the network calculus delay bound is tight, is worst case. Specifically, there exists a trajectory scenario where the input of the flow is equal to its arrival curve. The output of the flow is equal to its strict service curve. Then the worst case delay in this scenario, which is the horizontal deviation between the input and output of the flow, is exactly equal to the horizontal deviation of the arrival curve of the flow and the service curve of the system, which is equal to the network calculus delay bound. We have shown that the same result is valid for the weighted round robin strict service curve. So with constant packet sizes, weighted round robin also gives worst case delays. Very well, until now, we are sure that interleaved weighted round robin reduces the worst case delays. Let's quantify this reduction. First, we consider one configuration where we have 8 input flows with the corresponding weights. We assume constant packet sizes for all flows, then we are assured that all network calculus delay bound are worst case delay bounds. We also assume that we have a constant rate server with this rate. Given the simulation parameters, we can compute for each flow a blue curve, something like blue curve, which is an IWR strict service curve, and a red curve, which is a WR strict service curve. Then, if we generate some arrival curve, we can compute the corresponding worst case delays for IWR and the WR. Then the improvement is simply the differences between the WR worst case delays and IWR worst case delays. In this figure, in the y-axis, I'm plotting the improvement for all flows in the system, where flow 1 is the flow with the smallest weight and flow 8 is the flow with the largest weight. I'm also plotting the median of WR worst case delay to see how relatively we have improved. This is a simulation that we have done for one configuration. We repeat the same simulation for several configurations. We change the set of weights and packet sizes for configuration. Then we compute here improvement ratio, which is the improvement normalized to the median of the WR worst case delay. This is because the scale of the improvement and the delay bound depends on the values of the weight and the packet sizes. And by comparing the improvement ratio, we can compare the improvement in different configurations. So in this figure, in y-axis, I'm plotting the improvement ratio in percentage for all flows in the system, where flow 1 is the flow with the smallest weight and flow 8 is the flow with the largest weight. As you can see, IWR brings an improvement between 20 and 60% for all flows. Another observation is that we have better improvement, more than 50% improvement for flows with larger weights. And this is because flows with larger weights can participate in more cycles in interleaved weighted round robin, which gives them much smoother service that results in a lower latency. Very well, we have found a novel strict service curve for the IWR. We have shown that it is the best possible one and always improve to the best possible strict service curve of the WR. We also find the set of all non-dominated rate latency service curve for IWR. And we have shown that we obtain tight delay bounds for a flow with constant packet sizes. If you have any questions, we're happy to discuss them via email. Thank you very much.